Hello and welcome, George Kamiti here. Today we are going to look into design of connectors and we are going to check the beam to column connection using web crates. And we are being asked the following. Show that the double angle web cleat beam to column connection shown in the figure above is suitable to resist the design shear force of 400 kilonewtons. Assume that the steel is of grade S275 and that the bolts are M20 grade 8.8 into millimeters clearance holes. On the figure above, we have a column of serial size 356 by 368 by 177 universal column in grade S275. Here we have angle cleats of serial size 90 by 90 by 10 in grade S275 as well. And then we have a beam of serial size 610 by 229 by 101 universal beam in grade S275 still. The diameter of the bolt is 20 millimeters since this is M20. Therefore, M20 means that the diameter of the bolts are 20 millimeters each. The diameter of the bolt hole, that is DH, that will be 22 millimeters, which is 20 millimeters, the diameter of the bolt, plus 2 millimeters, which is the clearance, 2 millimeters clearance holes. The pitch of the bolt is 140 millimeters and 60 millimeters. So we have pitch of the bolt 140 millimeters and 60 millimeters. The edge distance E1 is 40 millimeters. This is the edge distance from the bolt to the end, 40 millimeters. And distance E2 is 60 millimeters and 50 millimeters. On the lower side, we have an end distance of 60 millimeters. On the upper side, we have an end distance of 50 millimeters. The thickness of angle cleat, that is TP, is 10 millimeters as shown here. That is the thickness of the angle cleat. Before we begin designing the following connectors, we must consider or we must check that the following conditions are met. The pitch should be greater than or equal to 2.5 times the diameter of bolt. So that will be 2.5 times diameter of bolt, which is 20 millimeters, giving you 50. This one is less than 140 and 60, which is the size of the pitch. Therefore, we can see that the pitch, which is 140 millimeters and 60 millimeters, is greater than 2.5 times diameter of bolt, which is 50, and therefore that condition is met. The second condition is that the same pitch should be less than or equal to 14 times TP, whereby TP is the thickness of angle cleat, that is 10 millimeters, and therefore 14 times 10, that is 140, and therefore 140 is equal to, this is less than or equal to, 140 is equal to 140, and the same 140 is greater than 60. Therefore, you can find that P is less than, P is 10 millimeters. It is less than 14 TP. 14 TP is 140 millimeters. E1, which is the edge distance, that is an edge distance of 40 millimeters, should be greater than or equal to 1.4 times diameter of bolt hole. And diameter of bolt hole is 22 millimeters. Therefore, when you multiply 1.4 by 22, you get 30.8. And therefore, E1, which is 40 millimeters, is greater than 30.8 millimeters. And therefore, that condition is also met. E2, that is the end distance of 60 millimeters and 50 millimeters, should be greater than 1.4 times diameter of bolt hole. So 1.4 times diameter of bolt hole, which is 22, is 30.8. And we find that E2, which is 60 millimeters and 60 and 50, are greater than 30.8. And therefore, that condition is also met. Both E1 and E2, that is the end distance together with, that is the edge distance together with the end distance, should be less than or equal to 11 TP, that is the thickness of angle cleat, times a constant E. Constant E is usually given by 275 divided by the design strength of steel raised to the power of a half, or the square root of the same. Since the angle cleats are in grade S275, the beam together with the column, all of them are in grade S275. It means that PY is also 275. Therefore, 275 divided by 275, that is 1. Square root of 1 is 1. Therefore, the constant is 1. Therefore, 11 times TP, which is 10, thickness of angle cleat, times 1, that gives you 110. And you find that E1 and E2, that is 40 millimeters, 60 and 50, are less than 110, and therefore that condition is also met. Therefore, it means that all fastener spacing and edge stroke end distances to fasteners are satisfactory. After checking on these end conditions, the next part will be checking the strength of bolts connecting cleats to supporting columns. So this is the angle cleat. We have bolts, 6 of them, which are connecting this cleat to the column. Therefore, we must check the strength of the bolts connecting the cleats to the columns. And we are going to begin with determining shear. We have 6 bolts, that is 1, 2, 3, 4, 5, 6. They are of grade 8.8 bolts. Hence, from table 4.2, AS, which is the effective area of bolt, is 245 square millimeters. PS, which is the shear strength of bolt, is 375 newtons per square millimeters. That information you get it from table 4.19. Therefore, the shear capacity of single bolt, that is PS, shear capacity of single bolt, will be given by effective area of bolt, that is AS, times PS, which is the shear strength of bolt, and that will be 245 times 375 newtons. We convert to kilonewtons, that is dividing and newtons by 1,000, or multiplying by 10 raised to the power of -3, therefore giving us 91.9 kilonewtons. Shear capacity of bolt group, since all the bolts are 6, we are going to have 6 times the shear capacity of one single bolt. And that is going to be 6 times 91.9, which is 551.4 kilonewtons. This shear capacity of bolt group is greater than the shear force, which is 400 kilonewtons. And therefore, 400 kilonewtons, Therefore, it means that the bolts are adequate in shear. After checking shear capacity, we are now going to check about bearing. The bearing capacity of bolt, that is PBB, will be given by DB, the diameter of bolt, times TP, the thickness of angle cleat, which is 10 millimeters, times PBB, whereby PBB is the bearing strength of bolt. And that is going to be 20, which is diameter of bolt, times 10, thickness of angle cleat, times 1000, which is the bearing strength of bolt. Then we are going to get the value of PBB, the bearing capacity of bolt, in newtons. To convert in kilonewtons, we divide by 1000 or multiply by 10 raised to the power of -3. And that is going to give us 200 kilonewtons. Since thickness of angle cleat, which is 10 millimeters, is less than the thickness of column flange, thickness of column flange of this serial size 356 by 368 by 177, you obtain it from Appendix B of the BS 5950. Therefore, it means that the bearing capacity of Cleat is critical. Therefore, the bearing capacity of Cleat, that is PBS, will be given by PBS is equals KBS, whereby KBS is the coefficient times DB, the diameter of bolt, times TP, the thickness of angle cleats, multiplied by PBS, whereby PBS is the bearing strength of the connected part. Bearing strength of the connected part. The coefficient is 1 multiplied by diameter of bolt 20, thickness of angle cleat 10, then the bearing strength of the connected part is 460. We are going to get the value of PBS in newtons. To get in kilonewtons, we multiply by 10 raised to the power of -3, and that is going to give us 92 kilonewtons. This PBS, bearing capacity of Cleat, which is 92 kilonewtons, should be less than or equal to 0.5 times coefficient KBS times end distance E2 times thickness of angle cleat times PBS. So that is going to be 0.5 times coefficient is 1 times end distance of 60 millimeters times T, which is 10, the thickness of the angle cleat, times PBS, bearing strength of the connected part, which is 460. You get the answer in newtons, converting to kilonewtons, multiply by 10 raised to the power of -3. And therefore, the bearing capacity of Cleat, PBS, which is 92 kilonewtons, is actually less than 138 kilonewtons, which is this part. And from there, we are now going to check the bearing capacity of connection. We have 6 bolts. Therefore, we are going to multiply 6 by PBS, which is the bearing capacity of Cleat. So that is going to be 6 multiplied by 92, and that's going to give you 552 kilonewtons. This 6 PBS should be greater than the shear force of 400 kilonewtons. And since that is the fact, it therefore means that the bolts are adequate in bearing. Then from there, we are going to check strength of bolt group connecting cleats to web of supported beam. Therefore, since bolts are in double shear, the shear capacity of each bolt, that is 2 PS is going to be equal to 2 times PS. We had the value of PS here. That is the shear capacity of single bolt. That is 91.9 kilonewtons. Therefore, 2 times 91.9 is 183.8 kilonewtons. The loads applied to the bolt group are as follows. We have the design shear force of 400 kilonewtons applied at this point, which is 50 millimeters end distance, and design moment of force times distance. Remember, moment is given by force times distance. Therefore, the force, that is the design shear force, is 400 multiplied by the end distance E2, which is 50. And we are going to get the answer in kilonewtons millimeter, since this 50 is in millimeters. And to convert the moment to kilonewton meter, we are going to divide 400 times 50 divided by 1000, or in simple terms, multiply by 10 raised to the power of negative 3. And that is going to give us a moment of 20 kilonewton meter. Therefore, the load on the outermost bolt, that is A1, this outermost bolt here, due to this moment of 20 kilonewton meter, will be given by, therefore, this force, FMB, force due to moment, will be given by MA divided by Z. And this formula is coming from what we call the bending equation. And from the bending equation, we know that the moment divided by the moment of inertia is equal to stress divided by y, whereby y is either depth divided by 2 or breadth divided by 2. And from simple stress and strain, stress is usually given by force divided by cross-sectional area. Therefore, when we substitute this stress here, we are going to have moment divided by I, which is the moment of inertia, which is equal to stress, which is force, over area, times 1 over y. Then we make force the subject, and by doing so, we are going to have force is equals moment times area times y divided by I. The section modulus Z is given by moment of inertia divided by y. And therefore, when we have y over I, it means that it is the reciprocal of the section modulus Z. And therefore, this means that our F will now be given by MA divided by Z. Therefore, that is now the formula of calculating the load on the outermost bolt due to this moment of 20 kilonewton meter. The section modulus, as we have said, is given by I divided by y. And moment of inertia in this case is equal to 2 times area of bolt, because we have because these bolts are in double shear. Therefore, we are going to have 2 times area of a bolt into summation of y squared. And this summation of y squared is distance of each bolt from the center. And this is where we have our center. Therefore, the distance of each bolt, the 3 bolts from this center, we have the first bolt having a distance of 30 millimeters from the center. Since this distance is 60 millimeters, half of it is 30, and therefore we have 30 squared plus the distance of this second bolt from the center is 30 plus this 60, which makes it 90. Therefore, 90 squared plus the distance of the outermost bolt from the center will be 30 plus 60 plus 60, which is 150 millimeters, and then we square it. By doing so, we are going to get a moment of inertia of 2A, whereby A is the area of bolt, multiplied by this section, that is squared plus 90 squared plus 150 squared, is going to give us 31,500. And therefore, 2A times 31,500 is equals to the 63,000 A millimeters raised to the power of 4. Then we have to calculate the value of y so that we can get the value of z and substitute it here. Y is the sum of the outermost, or is the distance of the outermost bolt from the center, and the distance of the outermost bolt from the center will be 30 plus 60 plus 60, which is actually 150 millimeters. Therefore, Z now will be given by the moment of inertia, which is 63,000 A divided by 150, which is Y. And that is going to give us 420 millimeters raised to the power of 3. Therefore, the load on the outermost bolt due to this moment of 20 kilonewton meter will now be given by moment, which is 20 times 10 raised to the power of 3. This 10 raised to the power of 3 is converting meters to millimeters. So that we can have kilonewton millimeter, but the kilonewton will remain. Therefore, we are going to have 20 times 10 raised to the power of 3 multiplied by this A, the area of bolt, divided by Z, section modulus, which is 420A. This A and this one are going to cancel out. And by doing so, 20,000 divided by 420, that is going to give us 47.6 kilonewtons. Therefore, that is the load on the outermost bolt as a result of the moment. Then from there, we are going to calculate the load on the outermost bolt, that is this bolt A1, due to shear, that is FVB. And this will be given by the design shear force divided by the number of bolts. And therefore, the design shear force is 400 kilonewtons divided by 6, which is the number of bolts that we got there. 400 divided by 6, that's going to give us 66.7 kilonewtons. Therefore, the resultant shear force of bolt, that is Fs, will be given by the square root of load on outermost bolt due to shear, which is 66.7 squared, plus the square of load on the outermost bolt due to moment, that is FMB, that is 47.6 kilonewton squared. Then we find the square root of that. And when we do so, we are going to have a resultant shear force of 82 kilonewtons. Since this resultant shear force of bolt is less than twice PS, whereby PS is the shear capacity of single bolt, we had it as 91.9 kilonewtons. We had calculated it earlier. And when you multiply 91.9 kilonewtons multiplied by 2, that is going to be 183.8 kilonewtons. And therefore, this means that the bolts are adequate in shear, since this one is less than twice PS. Then from there, we are going to have a bearing check, and we had calculated the bearing capacity of the bolt, that is PBB, which was 200 kilonewtons. And since it is less than the resultant shear force of 82 kilonewtons, then the bolts are okay. The bearing capacity of each bolt cleat, as we had already calculated, that is PBS, is 92 kilonewtons. Bearing capacity of both cleats, because we have two cleats on this side and on the other side of the column and beam, that will be twice 92. 2 multiplied by 92, that is 184 kilonewtons. This one is greater than the resultant shear force of 82 kilonewtons, and therefore it means that the bolts are okay when it comes to bearing. The bearing capacity of the web of the beam UB, that is PBS, will be given by KBS multiplied by dB, the diameter of bolt, that is 20 millimeters, multiplied by the thickness of the web, multiplied by the bearing strength. And therefore, this is going to be KB is 1, it is a coefficient, multiplied by the diameter of bolt, 20 millimeters, multiplied by the thickness of the UB section. This one is obtained from Appendix B of the DS 5950, multiplied by PBS, that is the bearing strength of the bolts, and it is 460 newtons per square millimeters. We are going to get the answer in newtons, and therefore to get the answer in kilonewtons, we are going to divide this by 1000 or multiply by 10 raised to the power of -3. And that is going to give us 97.52 kilonewtons. Therefore, since the bearing capacity of the web, PBS, of 97.52 kilonewtons is greater than the resultant shear force of the bolt of 82 kilonewtons, then the bolts, cleats, and beam web are adequate in bearing. After bearing checks, we are now going to determine the shear strength of the cleats. Shear capacity of a single cleat, that is PV, will be given by 0.6. PY is the design strength of steel, multiplied by AV, which is the shear area, and AV is given by 0.9 multiplied by A naught, which is the net cross-sectional area of cleat. And therefore, the net cross-sectional area of cleat, that is A naught, is given by thickness of cleat, which is 10 millimeters. That is the thickness of cleat, 10 millimeters, multiplied by the length of cleat, which is 400 millimeters. And therefore, the net cross-sectional area of cleat will be thickness of 10 multiplied by 400. Therefore, AV, the shear area, will be given by 0.9 times 10 times 400, and therefore PV, the shear capacity of single cleat, will be 0.6 times the design strength of steel, that is 275, since the steel is in grade S275. Then you multiply that by AV, whereby AV is 3600 square millimeters. Since 0.9 times 10 times 400 is 3600. We are going to get the answer in newtons, and therefore to convert to kilonewtons, we divide this by 1000 or we multiply by 10 raised to the power of -3. And that is going to give us a shear capacity of a single cleat of 594 kilonewtons. And therefore, since the shear force, that is a V divided by 2, remember we are talking of two cleats sharing a shear force of 400 kilonewtons, that is 200 kilonewtons, is less than the shear capacity of single cleat, 594 kilonewtons, then it means that the angle cleat is adequate in shear. Then from there, we are going to check the bending strength of the cleats. And we have said that for a single cleat, the shear force will be 400 divided by 2. That is the shear force of 400 kilonewtons then each cleat will be subjected to a shear force of 200 kilonewtons. Therefore, the bending moment is going to be 200 times the distance, that is the end distance of 50 millimeters. That is going to give us the answer in Newton millimeter. That is going to give us the answer in kilonewtons millimeter. So we divide this by 1,000, or we multiply by 10 raised to the power of -3 to convert millimeters to meters. The kilonewton still remains because this is 400 kilonewtons divided by 2. This is 50 millimeters, giving us the answer in kilonewton millimeter. So we divide by 1,000 to get the answer in kilonewtons meter, and that's going to give us 10 kilonewton meter. Then the moment capacity of one angle cleat will be given by PYZ, whereby PY is the design strength of steel and Z is the section modulus, which will be given by TP, which is the thickness of the angle cleat, multiplied by LP, which is the length of the cleat, and then squared. Remember, Z is usually given by BD squared divided by 6. That information, you can obtain it from Structures Module 1. And therefore, the breadth is the thickness of the cleat, which is 10. The depth of the cleat, which is the length of the cleat, is 400. We square that, then we divide by 6. And that's going to give us 266.7 times 10 raised to the power of 3 millimeters raised to 3. And therefore, the moment capacity of one angle cleat will be equal to the design strength of steel, which is 275 newtons per square millimeters, times the section modulus, 266.7 times 10 raised to the power of 3. And that is going to give us 73.3 times 10 raised to the power of 6 Newton millimeter. Converting that to kilonewton meter, we are going to divide this by 1,000,000, or we multiply by 10 raised to the power of -6. And that is going to give us a moment capacity of 73.3 kilonewton meter. Since this is greater than the bending strength of a Cleats, which is 10 kilonewton meter, then it means that the angle Cleat is adequate in bending. Then from there, we are going to check the local shear strength of the beam. The shear capacity of the supported beam, that is PV, is given by 0.6 PY AV, whereby AV, the shear area, is given by thickness of the web of the beam obtained from Appendix B of the BS 5950, multiplied by the depth of the beam section, also obtained from the same Appendix B of BS 5950. And that happens to be 10.6 thickness of the web multiplied by the depth, which is 602.2 millimeters. And that is going to give us a shear area of 6,383.3 square millimeters. And therefore, the shear capacity of the supported beam is now going to be 0.6 times Py, the design strength of steel, which is 275 newtons per square millimeters, times AV, the shear area. We are going to get the answer in newtons. For us to get the answer in kilonewtons, we are going to divide this by 1,000, or we multiply by 10 raised to the power of -3. And therefore, since PV, which is the shear capacity of the supported beam, 1053.2 kilonewtons, is greater than V, the shear force, the design shear force, which is 400 kilonewtons, then it means that the supported beam at the end is adequate in shear. And that marks the end of our today's lesson, marks the end of this question, and we appreciate for watching our video. all the way to this point. So if you are not yet a subscriber, hit that subscription button. Thank you. See you in yet another lesson.